Yeah, so thank you everyone for coming to this second lot of talks at the Open Programming Mini-Conf. Once again, sign up for lightning talks on the whiteboard at the back. I would really love it if we could fill that hour of the Mini-Conf. So our next presenter has been a distinguished engineer at IBM's Linux Technology Center for quite some time. He maintains the RCU implementation within the Linux kernel. He's going to give a talk on validating core parallel software. Please welcome Paul McKenney.
Thank you. So this is a little bit of, I hope you don't get nitrogen necrosis or bends from this. We're going from way up on the stack all the way to the bottom. And the trade-offs are a little bit different. And so we're going to take a look at what you have to do to get validation if you have deep in the bowels of the system parallel software that has to work and has a very large installed base. And one of the big things with that is validation. And there's a few things. We'll go through as many of these as we have time for. There's a number of ways of doing it. You need to use all of them. And probably, actually that's not true. You need to use all of those plus a bunch of them I haven't thought of yet, okay? But that's a start. Let's start with some definitions. Whether we like to admit it or not, the only bug-free program is a trivial program. A reliable program is one that has no known bugs. From these axioms, we can make a simple proof that says that any non-trivial reliable program, okay, non-trivial and reliable, has at least one bug you don't know about. If it had no bugs, it'd be trivial. If you knew about them, it wouldn't be reliable. Then we get one of these fortunately, unfortunately things here. Things have been getting better over time. I mean, you know, I like to reminisce about the old days as much as any other guy my age, but the fact is things have been getting better, at least in computing, sometimes. Fortunately, the size and complexity of a trivial program has been increasing sharply over the past decades. Unfortunately, that has not been increasing as fast as the typical size of a program. You win some, you lose some. One thing, no matter how you want to look at it, I assert the Linux kernel is not a trivial program. You may have a different opinion, but that's mine, okay? So what that means in this imperfect world is that validation is more about reliability than about perfection, than about total freedom from bugs. But the world may not be perfect, but it does have its advantages. You know, being in the world as opposed to not being in it, as near as I can tell anyway. Let's start with the open source way of avoiding bugs. And this is something that was a real surprise for me. I've still spent most of my career as a proprietary programmer. And this is much more effective than I would have expected. But it does have its limitations. Yes, to 10,000 eyes, all bugs are shallow. But how many of those 10,000 eyes are going to be looking at your code? And if they do look at your code, when exactly are they going to do it? And of those, how many of them are going to know enough about the specific little piece of the Linux kernel you're working on to be able to find the bugs you have in it? I mean, you do have bugs in it, okay? Get over it, you do. And the answer is probably not enough, although it's much, much better. I mean, there's some people that review my patches. I really appreciate it, some of them in this room. But, you know, we're all human and we all make mistakes, myself especially perhaps. Well, the thing is, review is not the only thing we do in open source. And in fact, the testing that people are doing has gotten really impressive lately. I mean, if I publish a new branch to my -RCU tree, there are people that go and grab that and automatically run tests on it. Not just on the tip of the branch, but on every stupid commit I have in my branch. Which is a good thing, because it means if some other poor guy has to get bisect sometime in the future, they have half a chance of, if they land in the middle of my stuff, having something that actually reasonably works. But nonetheless, you know, some people do test random patches, and including just the stuff I put out to my RCU tree, and sometimes even earlier. Some people test -next. Others maintainer trees, sometimes mainline, and some distro kernels. But you know, if they're waiting until it makes it a distro before they test it, well, I'd rather find the bugs before then. Although distro testing is important, don't get me wrong. And even if they do the testing, are they going to run the hardware and software configuration and the workload that's going to find your bug. Maybe they will, maybe they, I mean, eventually they will, believe me. I mean, eventually they're going to find it when you least expect it and when you're least able to deal with it, but they'll find it. The question is when. So open source is a wonderful thing. It's been much more effective at finding bugs than I've ever dealt with in proprietary days. But you know, if you're doing stuff that's way down in the bowels, that's being run on 100 million platforms throughout the world, you might want to be a little more proactive. I mean, it's great, rely on it, but you need more. One thing is to start at the design phase before you even have a patch. And so there's two basic things here. I'm going to go through this quickly. One is understanding the hardware. And that's easy for me because I'm down like right on top of the hardware. It's a little more difficult if you're up on top of the stack where you can get more productivity. And which in my case is easier because, again, I'm down on the bottom where there's not so much beneath me. A key thing if you're doing core parallel software down at the bottom of the stack is performance is a key correctness criterion. If your stuff doesn't perform, doesn't scale, it's buggy. Okay? Being functionally correct is only half the battle. After all, if you didn't care about performance, if you didn't care about scalability, why on earth are you writing parallel software? Just write a sequential program and be done with it. I'm not going to go through this in detail, but these are different timings. So we have constant nanoseconds in the middle column and the ratio to the clock period in the last column. And as you can see, instructions are not created equal. A simple register-register instruction might get done in 400 picoseconds at the top there. If you have a multi-socket machine down in the bottom in red, it's going to cost you more than 2 orders of magnitude more if you have a cache miss to some remote part of the machine. And again, since we care about scalability and performance down in the core of the machine, if we're doing parallel programming, we're going to have to be kind of careful to make sure we're using things up at the top of this chart where it's fast and not so much down at the bottom of the chart where it's slow. We're going to have to design our software to avoid the expensive operations. If we don't do that at design time, we're going to have just performance bug after performance bug and scalability bug after scalability bug, and our life is going to be difficult, no matter how much review or testing people do for us. And these are, I have a question there. The reason that they're best case is because this is only a 2-socket machine. And so the guys going off socket have only one place to go. If you had multiple sockets, there'd be have to be more electronics there to figure out where to send it. And it'd be slower. This is kind of a picture of a machine. And the problem is the speed of light is just too freaking slow anymore. I mean, light's been running around for eons, and now it's too slow. And I'm one of the people complaining about it, but so it goes. And the problem is that we don't use light inside computers. We use electrons. And electrons are even slower. They're about 30% the speed of light in a conductor on a chip. And about 3%, that's 3%, 1/30th, if you're inside of a transistor or other electronics on the chip. And so that means that the light's going to go about that far and back during a clock cycle. And the chips are bigger than that. And that's why we have those big numbers at the bottom of that previous chart, or one reason anyway. So if you did something silly, there are possible hardware workarounds to this, but if you have a straightforward machine, one that they have these days, and you do have a whole bunch of CPUs doing an atomic increment on the same variable, you can see the variable is going to have to kind of go running around the machine in that big red circle, like that. And it's not going to go faster than the speed of light. And it's going to take a long time. The more CPUs you have, the longer it's going to take. And that means that if you add CPUs to your machine, it'll run slower. And I don't know about you guys, but if I add CPUs to the machine, I kind of want it to go faster. If you structure your hardware to know about the machine and take advantage of where it's fast and avoid where it's slow, you'll do something like this, perhaps having a CPU have each. And this is done a lot in the Linux kernel, for example, in networking, where there's kind of per CPU counters. And so each CPU increments its own counter for a packet arrival, for example. If you want to do monitoring occasionally, you sum them all up. The monitoring happens rarely, the counting happens frequently. And you end up with little loops like this, and it doesn't take anywhere near as long for electrons and light to make a little circle inside a CPU as it does for them to bounce back and forth among all the CPUs. Now for incrementing, the hardware guys might be able to help us out. You can imagine them doing some clever circuitry that combines, is that they're all incrementing the same variable, to combine that up and send it up and eventually find the variable and say, hey, all these CPUs want to add this much, relying on commutative and associative laws of addition, and make things go faster. But still, even so, this is not going to be as fast as each CPU having its own variable and doing its own incrementing by itself. So one principle to apply at design time to avoid performance bugs is don't have just one of anything. Because if you just have one of something, the CPUs are all going to get piled up somehow or another trying to deal with that one thing. It's not going to go fast. Instead, you want to partition your program to have multiple things. And at that point, you'll have fewer collisions, and more of the work the CPUs do will be getting real work done, and less of it running into each other and trying to deal with the contention. So two ways of doing this in particular with synchronization primitives. One of them is cheap and cheerful. Have ways of reducing the overhead of the synchronization primitive. And of course, my favorite way of doing that is RCU, but there's a lot of other ones as well. Another way is if you're going to do some expensive synchronization, get your money's worth. Rather than, for example, having a lock guarding incrementing a single variable, which would be this little tiny bit for the critical section and a huge red part for the lock acquisition itself. If you have to acquire a lock, do something worthwhile. Structure your program so that you partition it as a high level in the application or the program as you can, so that when you go and do something, you're doing a large job, and the amount of time spent synchronizing is small compared to the size of the job. And you see this a lot in distributed programming. They call it sharding. The Googles of the world with MapReduce and things like that. It's really very effective, and it's something that can be applied at the lower levels as well. One important safety tip, you have to do both of these if you have a large real-world program. You both have to partition it carefully to avoid conflicts and contention, and you have to work to reduce the overhead of synchronization. You may need to do both of them in a given situation, or you may have to apply different ones in different parts of your program. You need more than one tool in your toolbox is what it comes down to. So, understanding the hardware will help. The hardware is going to change, and life's like that. You have to change software as hardware changes if you want to get the most performance and energy efficiency and everything else out of it. And that's one reason, by the way, why it's important to do regression testing. Because the hardware or software will change. You write the code, you put it out there, and somebody runs it on different hardware or software. Something will happen, it'll have to be fixed, and that's how you find out. Or at least one way you can find out. I'm not going to go through this very much. You have to understand the software, and there's a lot of it. We have these huge piles of software. Sometimes I feel that instead of premature optimization being the root of all evil, it's premature abstraction, but that may be just me. In any case, if you're doing on top of a large software stack, you're going to have a lot of learning to do to make it work optimally. And I'm lucky I'm down at the bottom. One thing that can help, this is how it looks in C code or pretty much any other language for a big set of structures. And you can work out that and figure out how it might fit together. But oftentimes drawing a picture can help understand it, help it keep in your mind, and also show you things about it you didn't see when you just wrote the code. And it's especially helpful if you're going into code somebody else wrote, which happens a lot. If you go and draw a picture of it and see how it fits together, sometimes it can help you find what's going on and what the problem is much more quickly than just staring at the code. This is just another piece of that same picture. A process can help as well. I think we'll do this one and call it good. Review from other people is the best thing. The cool thing about having other people review your code is they aren't stuck with the same stupid assumptions and therefore don't make the same stupid mistakes. They make a different set of stupid mistakes. And that means they can find your mistakes more easily. But still, reviewing your own code a little bit later can be very helpful. And we'll look at that in a little bit. Testing early and often is really helpful in small pieces. One way to look at it is that bugs come from interactions of software that you didn't anticipate. Interactions between software rise as the square of the size of the software. So the bigger piece you throw into your test jig immediately, the more trouble you're going to have trying to figure out where the heck the problem is that caused it to break. If you start with small pieces, get those working, and then combine them, you have a little bit easier time finding the bugs and fixing them. Use existing well-tested code. It's fun to reinvent the wheel, but it may not be the best thing to achieve productivity and reduce the number of bugs. Hopefully the stuff that's already out there is more thoroughly debugged, which may be a debatable proposition. This is something that is easy to say but hard to do when you're in there. Oh, this will be cool, we can just do this. But there you are. And I still have problems following that advice, and there's a URL if you want to check into that. These slides will be up at some point, I'm sure. So what I do, and again, this is, you may say, well, this takes a long time, and that's fine. And if you're working at the sequential code and it's something you test incrementally, some kind of a scripting language, you probably don't want to do this. It's probably better to type the things in, see if the little statements work, and then string them together. But if you're writing something that's deep into the bowels system, it's difficult to test separately. What you do is you write the code in pen on paper. And yes, this is how you had to do it back in punch card days, which were something that was really happening early in my career. You correct the bugs as you go. And since it's pen, you cross stuff out and write it again. Sooner or later, you get a piece of paper that's so messed up that you say, I can't read this, and you copy it over onto a clean sheet of paper. Now, the reason for doing it in pen, if you do it in pen, you can't lie to yourself about having got it right on this page, okay? So you keep doing that. You got this new sheet of paper, you write it cleanly, and you, oops, I made that mistake, you cross it out, and you do that again. You keep doing that until the last two sheets are the same. I mean, except for you may ignore the crossouts, but they say the same thing. Then maybe you understand what you're doing. I think we had a thing earlier about understanding the problem. Well, if the way I know I understand the problem or not is if I do the solution. And doing this helps me refine my understanding of the problem. So there was a certain function in RCU, and that's what it looked like. That's what the first sheet of paper looked like. You can see I didn't get very far before I realized I didn't know what the heck I was doing. So I started over, and I made it a little bit farther, but you can still see there's a lot more cross out than there is forward progress. You see, if I had just erased that or done it on the terminal and just hit backspace, I wouldn't have had that immediate feedback, Paul, you don't know what the hell you're doing, let's try again. And this time it actually looks like, maybe I know what I'm doing. I mean, there's not quite as much cross out, and there's a lot more code. And finally, this one is the same as the previous one, except that here I have crossouts and there I don't, but the stuff that's not crossed out is the same. All right, that's great. It felt good at that point. It's time to type in and test it. A natural question at this point is, how did I do? Well, the white stuff is stuff that is exactly in the working stuff that made the main line as it was on the sheet of paper. The red stuff is different. So you can see I added a couple of warn-ons. There's debugging stuff that I probably should have added in the first place, but it didn't affect the function. And I have no idea why I interchanged lines 25 and 26, but I did. I mean, it doesn't make any difference. I don't know why, but I did. Of course, you add more stuff to the program, and that means you need more changes. And the red stuff is more stuff that changed as a result of changing other parts of the code. There wasn't a huge amount of change, but when I added RCU priority boosting, this essentially got rewritten. So this can be a little bit, if you're not used to it, I guess if you haven't done punch card programming maybe, it can seem unproductive and difficult. But if you add in the time spent chasing down bugs, finding out where they are, it can make a big difference. It can make things go a lot faster. Again, when you're writing code that's fairly deep in the bowels of something where you can't just run a script and check the pieces out one at a time and string them together. But you know something? I do this for most of the RCU code, and there's still bugs in it. And there's a bunch of reasons this can happen. You can feel pressured by schedule and just say, I'm not going to do that. And obviously, then you won't find any of the bugs you would have found. It's often the case that I think I know a lot more than I do about both the hardware and the software and what the people want from me. And a particular thing was in IRQ not working the way I thought I did, which was kind of silly. I thought it told me whether I was an interrupt handler or not, which is stupid because it's a software thing. So there's a period of time clearly when you're an interrupt handler when it isn't saying it yet because somebody hasn't done the store. And that caused some problems. A big one is having excessive optimism about understanding the requirements. Understand the problem. Brady said this morning. Understand the problem. Well, how do you know whether or not you understood the problem? Sometimes it's obvious, but sometimes you have to implement it to figure out how stupid you were about the requirements. And sometimes that's life. The other thing is there's a bunch of things. Well, it's just a few extra microseconds, just more interrupts. I was in this camp in the middle one there. It's only a few extra schedule clock interrupts. And the embedded guys are screaming at me, "You're using up 30% of the battery, you idiot!" So, you know, it won't create scalability as long as you don't have more than 8 CPUs, which used to be rare, but not so much anymore. The thing is, though, is it's kind of a human nature thing. If you aren't excessively optimistic, as near as I can tell, you'll never start anything. In fact, there's a clinical term for people who are not excessively optimistic, and that term is clinically depressed. And clinically depressed people are actually excessively optimistic, just not as optimistic as not depressed people. So, you know, go figure. Anyway, we're getting towards the end. Mechanical proofs, I'll skip for the moment. Statistical analysis is just a way of things. Schedule pressure. Sometimes you've got a bug in the system already, and it's already breaking things. And so sometimes you've got to be just kind of throw the process aside, get the bug at least sort of fixed immediately. But you shouldn't make the same mistake I made. I did that early one year, and the bug fix had a bug in itself, which wasn't as obvious as the original bug. And so because I just failed to spend a few days after submitting the bug fix, you know, going through and carefully tracing out what was going on, I ended up spending like 3 months near the end of the year chasing the bug down. Okay, so yes, get a fix in there fast, but follow up and make sure that the fix is real. The statistics are that 1 out of every 6 fixes introduces a bug. Okay? And we don't like to remember that when we're fixing things, but that's the statistics. That's the way people work. So have a little respect for the bug fix. It may not be doing what you want. The other thing is you have to take on a long perspective. You can blame it on somebody else that they're schedule pressuring you, but you're the one that's deciding how to invest your time. You know, unless you have a really micromanaging manager, he's not, you know, sitting there grabbing your fingers and making the move on the keyboard. You're the one doing that. And you have to accept responsibility for that. Okay? So, you know, management has a lot to answer for, don't get me wrong. But don't blame your choices on management. The other thing you can do that's kind of a jujitsu trick is align with management initiatives. I mean, these guys don't like bugs any more than you do. And so they have these things like agile development was one a couple of years ago, or any other number of other buzzword things. Align with those. I have to do this because it's the agile way of doing it, you know. That can sometimes help. I did all this and there's still bugs. Yeah, well, you know, welcome to the real world. The purpose of validation is not to make a perfect program. If you want a perfect program, write a trivial program. That's all I can tell you, okay? The idea is to reduce risk. Yes, we should strive for perfection. You know, that's what you want to try to make things perfect. But understand, you know, don't let the imaginary perfect be the enemy of the useful good. The idea is to do good in the world. And you can't do that by just sitting around and waiting for something perfect to show up. And even if you know the bugs are inevitable, you still have to fix your bugs, okay? Just because you know you're going to make some doesn't mean you're not supposed to fix them, or you can get away not fixing them. With that, we've all warned of bugs. You know, you can if you do tracing, you have to reduce the data somehow, make the computer do that. We've gone through all this. There may be some bugs. You may have to fix them. There's a bunch of ways of avoiding it. This slide is sponsored by IBM Legal. And we might have time for questions or might not. I'm not sure.
We've got some time for questions while our presenters swap over. So if you could raise your hand so I can see you if there are questions. Well, apparently there aren't any questions, so could everybody please thank Paul for his talk.
paradigm you're in to people outside of that paradigm? Because, I mean, in the areas that I work in, I say I'm able to choose some of my failure modes, and I'm happier with these failure modes than those failure modes. But then, how do you go about communicating effectively risk to people that don't have your kind of insights and knowledge and decision-making and skills?
There's a number of answers I give to that. The biggest thing is to build trust. If they know you and trust you, they'll at least listen to you, okay? And the other thing is that most of the time, I don't know who you're communicating with, but I can imagine management, I can imagine certification agencies, I imagine customers, users. All those people have risks that they're worried about that you probably don't know about. So an important part of building trust is to listen to them and try your best to understand the risks that they're worried about that may not be visible to you. If you're listening to them and you're understanding what their concerns are, they're much more likely to return the favor and listen to you and understand what your concerns are. Does that help?
Thank you.
Okay, thank you all very much, and hope this is helpful, and have a great rest of the conference.